Hi, and welcome to part one of my talk on L-spaces in instanton Floer homology. As an outline of what I'm going to do in this part, I'm going to first remind you what the L-space conjecture is. Then I'll introduce instanton Floer homology, the version of Floer homology that I want us to think about this conjecture. I'll discuss the properties of a version of that called framed instanton homology, I-sharp. And then I'll discuss a class of interesting manifolds from this perspective, which are called SU2 abelian. So to recall what the L-space conjecture is, Boyer, Gordon, and Watson suggested that if you have a rational homology 3-sphere Y and it's irreducible, then the following should be equivalent. First is that it should be an L-space, meaning that the hat version of its Heegaard Floer homology is as small as possible, that the dimension of it is equal to the order of the first homology of Y. Equivalently, the fundamental group should not be left orderable, and both of these should be equivalent to Y not having any co-orientable Tott foliations. It's been proved in a number of cases. For example, Boyer, Gordon, and Watson proved it for 7 out of the 8 Thurston geometries, all of them except the hyperbolic one. Henselman, Rasmussen, and Watson proved it for all graph manifolds. And it's been done in other cases as well, but for a general strategy, there's this problem, which is that we don't know really what HF hat has anything to do with pi 1 of Y. On the other hand, instanton Floer homology is by definition much more closely related to the fundamental group. So the general idea is we take a 3-manifold Y and a principal SU2 bundle P. There should only be the product bundle up to isomorphism, but that's just to give it a name. And we let script A be the set of SU2 connections on this bundle, and script G, the gauge group, be the automorphisms of this principal bundle. Then there's a Chern-Simons functional CS on the quotient A mod G. It's circle valued, it takes values in R mod Z, and it has the following interesting properties from the perspective of Morse theory. One is that the critical set is identified with the flat connections on P, up to gauge, up to automorphisms. And the other is that if you look at downward gradient flow lines of this functional, like you would in Morse theory, these correspond to 1-parameter families of connections on Y. And if you think of them as connections on R times Y, then they give you anti-self dual connections. This was a family of connections that was very well studied in the years leading up to this. So roughly speaking, you do Morse homology on this infinite dimensional space, and that's what you call the instanton homology. Another way to think about the generating set is to take the holonomy of a flat connection. If you have one of these generators, a connection A, then you can look at the holonomy around any loop, and it only depends on the homotopy class of the loop. So that gives you a representation from pi 1 of Y into SU2. And since we're taking connections up to gauge, we get representations up to conjugacy. So if we prove a non-vanishing theorem for the instanton homology, then we've learned something about pi 1 of Y. One big example was a theorem by Kronheimer and Rivka in 2003. They proved that if you take a non-trivial knot in the 3 spheres, let's call it K, then the instanton homology of one surgery on K is non-zero. And that means that there's a non-trivial representation from pi 1 of this one surgery into SU2. And in particular, if there's a non-trivial representation, it has non-trivial image, so that one surgery can't be simply connected. And that means that it can't be homotopy equivalent to the 3-sphere. And this was the so-called property P conjecture. This was the last step needed to prove it for all knots in S3. So then you might ask, well, given this connection, why don't we reformulate the L-space conjecture using instanton homology instead of Heegaard Floer homology? And one issue is that it's not obvious how to even state the conjecture in general, because instanton homology is only defined if one of 2 things holds. Either we have an integer homology 3-sphere, or we have an arbitrary 3-manifold Y, and we take an SO3 bundle P over it with odd second Stiefel-Whitney class. Both of these conditions are there basically to make sure that we don't have any reducible flat connections other than maybe the trivial one, if it's a product. And the reason we need to do that is that reducible flat connections cause problems in defining the chain complex proving d squared equals 0. So when we have a rational homology sphere that isn't an integer homology sphere, neither of these situations hold. But one thing we can do, and Kronheimer and Rivka defined a new invariant this way, is we can define the framed instanton homology by taking Y and optionally some multi-curve lambda inside Y, and we form a bundle Y over Y plus the 3 torus. And the way we define this bundle P is that its second Stiefel-Whitney class should be Poincare dual to the sum of lambda, the multi-curve on Y, and then just some circle factor of the 3 torus. And having that circle factor there is what makes the second condition that W2 is odd be satisfied, so that we actually have instanton homology. And we call that I-sharp, the framed instanton homology of Y again, with the multi-curve lambda. And just as a remark, this instanton homology is about twice as big as it should be. There's an involution that acts freely on it. And so really, if we want to define I sharp, we take the fixed set of that involution, whatever that is. So this was studied a bit by Chris Caduto, who proved that it had a lot of things in common with HF hat. For example, if you have a smooth cobordism between three manifolds, and maybe a smooth surface inside there connecting the multi-curves lambda, then you get a homomorphism on I sharp. And the way you define it is you count index 0 anti-self-dual connections over the cobordism, or over a completion of it. In the same way as the differential would be defined by counting such connections over the product R times Y. If you have a framed knot K inside Y, then there's a surgery exact triangle relating the original Y, 0 surgery on K with respect to that framing, and 1 surgery on K with respect to that framing. And you have to be a little careful about the multi-curves, but it's essentially the same story as in Heegaard Floer homology. It has a Z mod 2 grading, and the Euler characteristic with respect to this grading is always the order of H1. Again, that's the same in Heegaard Floer homology. For rational homology spheres, this is some integer, and if B1 of Y is positive, in other words, if the first homology is infinite, then we just declare this to be 0. And so we define a rational homology sphere to be an instanton L-space if the dimension of the framed instanton homology with rational coefficients is equal to that order of H1. In other words, if it's as small as it could possibly be. So you can ask now, what does it mean to be an instanton L-space? Well, if we think about it in terms of the chain complex, we've said algebraically that the generators of this complex are the same as flat connections on this bundle P up to gauge. And that gives us a holonomy representation of pi1 of Y plus the 3 torus into SO3. And we don't really want the 3 torus to be in there. We want pi1 of Y, but we can think about what this means, again, algebraically. So here's a picture. Y has been connect summed with the 3 torus here. And the obstruction to lifting this representation to SU2 is exactly given by this dual of the Stiefel-Whitney class, which was this circle factor. So we can identify the generators with representations of the fundamental group of Y plus T3 minus that circle into SU2. And the reason it's supposed to give us an obstruction is that rho of the meridian of that circle has to go to minus I. So it doesn't actually lift to an SU2 representation if you try to fill that back in. And again, this is done up to conjugacy, in other words, up to the gauge group. And if we think about what this means, well, we have any representation at all on Y. So we get all of hom from pi1 of Y to SU2. And then we can use this conjugation entirely on the T3 side. And there are 2 such representations of pi1 on the 3 torus up to conjugacy. So we get really 2 copies of hom from pi1 of Y to SU2. And so if that representation variety is as simple as possible, that's a good candidate for an instanton L-space, because it should give us as few generators as possible for the chain complex. So with that in mind, we define a 3-manifold to be SU2 abelian if every representation from pi1 of Y into SU2 has a abelian image. In that case, well, we might not have a discrete set of SU2 representations, so we might not be able to define the Morse complex, but we can do the next best thing if it's somehow Morse bot. So if we have an SU2 abelian manifold and Chern-Simons is Morse bot non-degenerate, well, we know from the previous slide that the homology of the critical set is just 2 copies of the homology of the representation variety of Y itself. And if there are only abelian representations, we can compute by an exercise that the homology of that representation variety is just Z to the order of H1 of Y. Essentially that all of the components of this representation variety are points in 2 spheres, and you just have to count how many of each there are. And then again, we get 2 copies of that because there were 2 points. So if the Chern-Simons functional was Morse bot, then there's a Morse bot spectral sequence saying that if we just look at the ranks of the E2 and E infinity pages, we get twice the order of H1 of Y is at least as big as, well, the instanton homology, which remember was twice the rank of I sharp of Y because of that involution. And so in that case, this rank inequality is telling us that we have an instanton L-space. So just to restate, if Y is SU2 abelian and this non-degeneracy condition holds, which we can restate in terms of pi1 of Y being what's called cyclically finite, that tells us that Y is an instanton L-space. So here are some examples of SU2 abelian three-manifolds. First of all, there's lens spaces. They have abelian fundamental group, so any representation of that into SU2 has abelian image. A little harder to see is we can take the -237 pretzel knot and do 37/2 surgery on it. This was discovered by Nathan Dunfield sometime around 2004. And you might notice the slope is interesting because this pretzel knot has lens space surgeries of slopes 18 and 19, and the slope is right in the middle of those. There's a family of examples discovered even earlier by Motegi, where you take a pair of torus knot exteriors, any torus knots you like, and you splice them together by gluing the meridian of one to the Seifert fiber of the other, and vice versa. And actually, it turns out Dunfield's example is a special case of this, where you glue left and right-handed trefoil complements together. Some examples that Raphael Zentner and I discovered are Seifert fibered spaces. You can either have a base orbifold S2 with cone points of order 2, 4, and 4, or you can have base orbifold S2 with cone points of orders 3, 3, and 3, as long as the first homology has even order. So those are all SU2 abelian as well. And if you have any of these examples or any others, you can connect some a copy of RP3 and it's still SU2 abelian. The reason being that pi1 of RP3 is just Z mod 2, and representations of that into SU2 have to have image in plus or minus the identity. So if you had only abelian representations of Y, then adding plus or minus the identity into the image isn't going to change that. And not all of these are cyclically finite. Most of them are, but some of these Seifert fibered examples actually aren't. Even so, all of these examples are actually instanton L spaces. And there are plenty of instanton L spaces that aren't SU2 abelian as well. So some examples will be coming up in a moment. But I should just mention, first of all, that this is sort of a generalization of the Poincare conjecture that's still open. Are there any integer homology three spheres other than the three sphere itself that are SU2 abelian? This is problem 3.105a in the Kirby list. And if you had such a three manifold, that would be an L space as well. But this is interesting. It's sort of a generalization of the Poincare conjecture, because you want pi1 to not only be non-trivial, you want it to have interesting SU2 representations as well. So some examples that aren't necessarily SU2 abelian include, there's the Poincare homology sphere. This one has finite pi1, and there are two conjugacy classes of non-abelian representations into SU2, so it's not SU2 abelian. Other ones are branch double covers of any quasi-alternating link in S3. This was proved by Scuduto, who really proved that there's a spectral sequence from odd Kovanov homology to I sharp of the branch double cover. And if the odd Kovanov homology is as simple as possible, for example, if L is quasi-alternating, then that tells us as a result that I sharp of the branch double cover has to be simple as well. So what does this cyclically finite condition mean? Well, what it means is that all of the finite cyclic covers of Y, other than the ones of maximal even order, have to be rational homology spheres. And there are cases where this holds automatically. For example, if the first homology is cyclic with order of prime power, then it's automatic. For surgeries on knots, we can actually understand this completely in terms of the Alexander polynomial. So the characterization turns out to be the following. If we have P over Q surgery on a knot K, and that's SU2 abelian, and if the Alexander polynomial of zeta squared is non-zero, whenever zeta is a pth root of unity, P being the numerator of the slope, then Y is an instanton L space, because that condition on the Alexander polynomial is exactly what it means to be cyclically finite. So here's some motivating examples for surgeries on knots. Well, there's the cyclic surgery theorem, which is a big theorem of Kuller, Gordon, Lukey, and Shalin, and it applies much more generally. But one thing they proved is if you have any knot in S3 other than a torus knot, then there are at most two non-trivial lens space surgeries. And in fact, they have to have integer slope. And if there's two of them, they have to be consecutive integers. And from the perspective of gauge theory, maybe it's sort of hard to understand lens space surgery specifically, but you could say, what's the gauge-theoretic version of it? You could say, does a knot have SU2 abelian surgeries? And if it's a torus knot, it has infinitely many lens space surgeries, so there are infinitely many SU2 abelian surgeries. But if there's a non-torus knot, we don't know how many it can possibly have. Is there a finite maximum? Can there be infinitely many? In fact, the best we know right now is there are two examples of knots with 3 SU2 abelian surgeries. There's the -237 pretzel again, And there's a twisted torus knot, which is a closure of this 4-stranded braid on the right. You take 4 strands, you do 7 quartered twists on them, and then you do a full twist on 2 strands at the end. And then for this one, there's lens space surgeries of orders 30 and 31. And then there's another one of these toroidal surgeries, these examples that Motegi came up with slope in the middle at 61/2. So a couple years ago, Raphael Zentner and I proved that if you have a non-trivial knot in S3 with infinitely many SU2 abelian surgeries, then it's possible that these are SU2 abelian, but pi1 isn't cyclically finite. We can't rule that out, but actually we know that at least one of these infinitely many has to be an instanton L-space. So suddenly it's interesting to say, what are the knots that have instanton L-space surgeries? Because they'll tell us something about questions like this. So again, there's the statement of the theorem, and here's a sketch of how we prove it. So what you do is you look at the representation variety, not of the surgered manifolds, but of the knot complement. And you say, for all these irreducible representations, you can always conjugate them so that the meridian and the longitude go to diagonal matrices with eigenvalues e to the I alpha and e to the I beta. And so you look at the pairs alpha and beta mod 2 pi, and you can plot them like I've done here in this corner of the slide. This is for the right-handed trefoil. You get 2 lines, open line segments really, of slope 6, which I've drawn in red. And now what does it mean to have an SU2 abelian surgery, say of slope 5 in this case? Well, I've drawn a line of slope 5. It's this blue dashed line in the picture, and the point is that they don't intersect. So if P over Q surgery is SU2 abelian, then all of these red points here that correspond to representations of the knot complement have to avoid the line P alpha plus Q beta is 0 mod 2 pi. Because anytime you have a point on that line, it says that mu to the P, lambda to the Q goes to the identity. And so this descends to a representation of the surgered manifold, which if it were irreducible to begin with, then the representation of the surgered manifold is also going to be irreducible. And so, it's one thing to avoid a line of one slope, like slope 5 here, because 5 surgery on the right-handed trefoil is actually a lens space. But if it happens for infinitely many different slopes, then this is a very strong constraint on this red curve, this image of the character variety of the knot. And it turns out that it's such a strong constraint, in fact, that all of these red points have to lie on finitely many lines of the same slope. So that's a very strong constraint on this image here. And actually, you can prove even more that the slope has to be rational. And if you write these lines as beta equals R alpha plus some constant S, then S has to be a rational multiple of 2 pi. So just looking at this picture on the right again, here's again, the blue line is what you have to avoid to have an SU2 abelian surgery of slope 5. For that right-handed trefoil, 11/2 surgery is also SU2 abelian. It's also a lens space. And so it misses this curve here in orange. And for slope 17/3, 6 minus a third, again, that's a lens space. And so it misses these lines of slope 17/3. And in general, if you're in the situation where the character variety of the knot has this image with, it looks like these finitely many lines with rational coordinates, then you can prove that the pairs alpha and beta in red here, and that come from the knot, actually avoid all lines of the form beta is something times alpha, where that something is the form R plus 1 over m times n, and m can be any integer. And so each of these slopes, R plus 1 over mn, is itself an SU2 abelian slope for k. So we've gone from knowing that there were infinitely many to knowing that there are infinitely many of this particular form, R plus 1 over mn. And you can always pick m if that's the case, so that the numerator is prime, and then you've got an SU2 abelian surgery with prime numerator, and we know it's automatic that cyclic finiteness follows. So then that surgery is an instanton L-space. And just on the right now, I've shown all of these lines at the same time of slopes 5 and 11/2 and 17/3. And you can see that they're starting to fill up more and more of this square. And so that leaves very little room for the representations of the knot complement itself, the part that's in red. So that's sort of where this constraint comes from, that it has to lie on finitely many straight lines. So here's a theorem that Baldwin and I proved recently. And a lot but not all of what follows is going to be joint with John Baldwin. that says a lot about the kinds of knots that have instanton L-space surgeries, like the ones with infinitely many SU2 abelian surgeries. So if we have a non-trivial knot and it has an instanton L-space surgery of some positive rational slope, any slope at all, then the following has to hold. K has to be a fibered knot and it has to be strongly quasi-positive. And any S surgery, again, S being rational on K, will be an instanton L-space if and only if S is at least twice the genus of K minus 1. So I'm going to talk about the proof of that in the second half of this talk. These are not surprising results if you know Heegaard Floer homology, because all of these statements were already known for Heegaard Floer L-space knots. So they're due to Ojvath and Szabo, Gigini and Ni, and Hedin in various parts. So here's a corollary. If you have a knot K and you take any slope P over Q of absolute value less than twice the genus minus 1, then pi 1 of P over Q surgery on K always admits an irreducible representation into SU2, except possibly if this cyclic finiteness condition fails. So if some pth root of unity satisfies, well, the Alexander polynomial at that root squared is 0. And this is, in some sense, a big generalization of a theorem of Pronheimer and Rivka from 2004. They proved that there are always irreducible representations of P over Q surgery as long as P over Q's absolute value is at most 2. But they proved it without restrictions on the Alexander polynomial. Here's another corollary, just following up from a couple slides back, that any knot with infinitely many SU2 abelian surgeries, well, it has an instanton L-space surgery, so it must be fibered and strongly quasi-positive. And here's a third corollary, that if K has the same A polynomial as some torus knots, either the trefoil or TPQ, where P and Q are both odd primes, then K has to actually be isotopic to TPQ. So the A polynomial detects infinitely many torus knots. And here's just a very, very brief sketch of the argument. Well, first of all, what is the A polynomial of a knot K? It's something that captures the SL2C representations of the knot group. Essentially, what you do is you look at all irreducible representations of the knot group into SL2C, which send the meridian and the longitude to diagonal matrices. So these have eigenvalues M for the meridian and L for the longitude. And you just look at all the pairs M comma L that come from eigenvalues of these matrices. And this gives you, in fact, some curve plus possibly finitely many points in C star squared. And the A polynomial is really just the defining polynomial of that curve in the complex plane. And I mean, this is slightly inaccurate. You have to throw out all the points, take the risky closure, but essentially that's how the A polynomial is defined. And originally the A polynomial also included a curve of reducible representations, and I'm doing a slight modification where we just throw that curve out. So the basic idea is, well, this is something about SL2 representations, but if K has the same A polynomial as a PQ torus knot, then in particular, SU2 representations are SL2 representations. So they all satisfy this constraint that M looks like e to the I alpha and L looks like e to the I beta, where PQ alpha plus beta is 0 mod pi. In other words, they lie on these lines of slope PQ. And this says, by the argument from a few slides back, that K has to be an instanton L-space knot. And so we know from properties of this that K is fibered, that the slope P times Q has to be at least twice the genus of K minus 1. And then we just throw in some geometric arguments. We know it can't be hyperbolic. It has to be a satellite knot. Since it's a satellite knot that's fibered, we know something about the pattern and the companion and so on. And without too much extra work, it falls into place. So those are some applications of this result. In part 2, like I said, I'll talk about some new formal properties of framed instanton homology and how they're used to prove this and some other related results. Thanks for watching.